Hello. Black holes today, that's the focus. So we're going to look at a few different things that occur before the formation of a black hole, what the black holes do, and the structure of a black hole. We're going to look at an equation that involves a black hole. We're going to look at active galaxies, which are linked to black holes, and also what might happen to stars that don't quite turn into black holes as well. So we're starting with active galaxies here. This says what are they and why are they so bright. You might not be aware of the term an active galaxy, but when we were first trying to gain information about galaxies and we would look at how bright they are, you would think that it'd be pretty obvious how bright a galaxy should be. Let's say a galaxy has 200 billion stars in. It's not too hard to estimate how many stars are in a galaxy. So let's say there's 200 billion stars in a galaxy. You would take the average brightness of a star, multiply it by 200 billion, and that would be the brightness of your galaxy. So for normal galaxies, that seems to be true, but for active galaxies, it's much brighter than would be expected. That's why they got called active galaxies. And it was a while before we figured out why they are so bright. It turns out black holes are the answer, but not the type of black hole that you've learnt about so far. So here's a galaxy that is similar in structure to ours, and this is just summarising what I've just said there. You can pause that and copy that down if you want. And this is Centaurus A, famously an active galaxy, and this is giving off way more radiation than it should. Now the term bright typically refers to visible light, doesn't it? But sometimes in this topic, when we say something is very bright, it might be giving off huge amounts of other parts of the electromagnetic spectrum as well. So it's not always visible light that's the main thing. And of course we study all parts of the electromagnetic spectrum for astronomy. So here's a black hole, an artist's impression of a black hole. It's originally thought that black holes would be impossible to ever find because they were so, just disappear in the blackness of space. But Stephen Hawking gave us a lot of work towards how we could find them, and now they're easy to find, and we found loads of them. Well, I'll just recap the life cycle of a star. So everything starts in a nebula, a big dust and gas cloud. And then in part of it, gravity starts to bring matter together, which would give you a protostar, not yet nuclear fusion. But then nuclear fusion begins, and that's where stars have most of their life in the main sequence. Now, depending on the size, it will either expand to a red giant or a red supergiant after a small period of contraction. Some of them actually expand, contract, and go through a number of cycles with that, but eventually they will collapse in on themselves, and then you get a little shock wave out if it's a red giant, or you get a huge shock wave out if it's a red supergiant, and that huge shock wave is the most powerful thing in the universe, a supernova. Now at the center of the explosion from a red giant, you have a white dwarf, and this nebula left over is a planetary nebula. But at the center of a supernova, you'll have one of two things. That's the Crab Nebula, which is a supernova remnant. So one of two things. Here they are. Oh, before we see those, just a word on the supernova. So as it does go supernova, as we said, the most energetic thing in the universe, that explosion can sometimes give off huge amounts of gamma rays, known as a gamma ray burst. Now, the gamma ray burst can be considered quite dangerous for a couple of reasons. It's a huge amount of energy. It gives off more energy than anything else in the universe. And if in the form of gamma rays, if it was a long way away and spread out, it wouldn't be a problem. But they tend to be highly focused. And that's the issue with gamma ray bursts. And it has come up a couple of times, a mention of these things on the exam. So you just need to be aware that it's a huge amount of radiation in the gamma ray spectrum, and they are, or tend to be, highly focused. So if you're in the focus of it, that means trouble. It means there's less chance to get hit by any of it. But yeah, if you're in the gamma ray beam, I suppose that's trouble. So if some gamma ray burst occurred close enough to us within our own galaxy and was focused upon the Earth, some people believe that would cause a mass extinction event. So yes, something to very much be aware of. Okay, so these are the two objects left behind after your red supergiant goes supernova. The smaller of the two would be, well, smaller stars would be the neutron star. Obviously, the very smallest stars end up as a white dwarf, so I suppose we could call them the middle-sized stars. They will end up as a pulsar. Now, pulsar, if you were to sit on a wheelie chair that spins and spin yourself around, stick your legs out as far as you can. Obviously, don't do that if you're going to hurt yourself or fall off, and I take no responsibility for any injuries, so I'm not encouraging you to do this. But if you were, and then you slowly bring your legs in, so you can tuck your knees under your chin maybe, then you find you'll speed up. You'll spin faster and faster and faster. Conservation of angular momentum. Now, a neutron star does that. Imagine it's a big star that shrinks down to the size of Greater Manchester, really. And as it spins, it spins faster and faster and faster as it contracts. Now, they give off huge amounts of radio waves, but there's a huge amount of energy that beams out from the poles. So if it's aligned in such a way where the poles are spinning and then they point towards the Earth once every rotation. So let's say this thing spins 100 times a second, then you'd get a little flash, a little burst of radiation 100 times every second. So it'd be pulsing 100 times a second. So they observed these stars that were pulsing, and you know, they all had these different frequencies that were measurable. I think it was Jocelyn Bell in Northern Ireland. She figured it out, and what they actually are neutron stars. So the pulsar turned out to be a neutron star. So imagine as a star collapses, the massive, the gaps between the nucleus and the electrons. Remember, you learned early on, I suppose, year 10, that every atom is mostly empty space, so everything is mostly empty space. Essentially, the empty space is knocked out of existence. So it's made of pure neutronium, just neutrons with no real gaps in the middle. The neutrons don't repel each other or attract each other, so there can be just no real gaps there. So it's incredibly dense, and you might learn that fact in year 10 that if you remove the empty space out of every person on the planet, they could all fit into a coffee cup. And I think we've been using that fact since the population was about 2/3 of what it is now. So I don't know whether it's expanded to one of them Sports Direct mugs or not. I haven't really done the calculation myself. But the funny thing about that it would still weigh the same as all the people on Earth. And that is the density of a neutron star. Unbelievable. If it's an even greater star than that, an even more massive star than that, it will collapse past the neutron star stage, and you will reach the point where it's a black hole. Now, the simple explanation of a black hole is something that's so dense nothing can escape, not even light, but that won't get you any marks in an exam. So a simple diagram of a black hole looks like this. The centre of a black hole is known as a singularity, a point of infinite density and zero size. The edge of a black hole is known as the event horizon. Any event is beyond our horizon that occurs within there, as in we will never know anything about it. You could send a probe in, and it could send radio waves on its way out, but they never escape, because if light can't escape, radio waves can't escape. Einstein explained it with it curves space-time on itself, essentially, and then it curves it back in on itself beyond the event horizon. So there's two definitions here. Inside the event horizon, the escape velocity is greater than the speed of light, but the event horizon is the point where the escape velocity equals the speed of light. So essentially, light would just really go round in a circle. That would be its best effort at escaping. Just outside of the event horizon, on the outside of the black hole, it is possible to escape, but only just. And as you go further out, obviously, it gets easier and easier to escape. So those are the two key terms, I would say, that crop up in the exam. So knowing how to explain how to define a black hole, I suppose, which is that thing, it's escape velocity greater than the speed of light, and then if they mention the event horizon as well. And you could be asked to draw a diagram. It's an incredibly simple diagram, considering how complex a black hole is. Okay, I just wanted to give a mention to one of my favourite terms in science, which is spaghettification. I don't know why it's my favourite term. It's quite a horrible idea, I suppose. But the idea is, as you go towards a black hole, the gravity starts to increase at such an incredible rate that the gravity on your feet, if you went in feet first, would be so much greater than the gravity on your head that you would be stretched into spaghetti. And that is a term that they use, spaghettification, which would occur. Alright, I won't go on about that though. So, I know that we haven't quite answered the active galaxies bit. So, collapsed stars, which have been a red supergiant and go supernova, they form what you call stellar mass black holes. They've not took on extra mass. If our sun, which it can't and it won't, but if our sun turned into a black hole, it wouldn't be any heavier. It would just be smaller, so therefore more dense. They're incredibly dense, but they don't have to be incredibly heavy. So those are stellar mass black holes. They have the mass of about a star. Goes up to about 30 stellar masses. But there is another type of black hole, which we haven't mentioned yet. That's a supermassive black hole. Way bigger than the stellar mass black holes. Okay, here's a little article about one that was discovered in 2011. Billions of times bigger than our sun, so billions of stellar masses. So they're thought to be at the centre of galaxies. And they give off huge amounts of energy, which seems strange for a black hole that absorbs everything and doesn't give anything off. But if the black hole is ripping things apart and out of existence, then as things are ripped apart or as they are going into the black hole, that's when huge amounts of energy can be given off. About 10% of black holes will have jets, which, just like we talked about the gamma ray burst, they kind of focus this energy to a point. And actually, depending on the angle that we look at these jets, we used to think they were completely different objects. But that's the answer to the active galaxies. Active galaxies are thought to have supermassive black holes at their centre, which gives off huge amounts of radiation, and that's why they're brighter than they should be. And there's an example of the jets there. So, active galaxies, don't really need to worry about this, but they can be split into 4 types. But I just wanted to mention that, well, it depends on how you look at them, you see. So this is what we were saying. It's the same thing looked at from different angles, and they were thought to be different things. It's nice when you can do a bit of unification in science. And I suppose when they worked out the blazar, the quasar, the Seyfert 1, the Seyfert 2, and the radio galaxy were all the same thing, just looked at from a different angle, it made things simpler. It's nice when stuff gets simpler. So, one of those 4 categories that I wanted to mention is the quasars. Now, the quasars are thought to be the most energetic things in the universe that are just not an explosion. And quasars are active galaxies on the very edges of our universe. When they were first discovered, interesting story about them, they were thought to contain new elements. Which is funny because, well, they were incredibly bright, you see. And when they were detected, we just assumed that because they were so bright, they must be quite close. Nobody, for a second, thought they'd be on the edge of our universe, because they were so bright. You can't see things on the edge of our universe very easily, and if you can, they're very, very dim. And this turned out to be incredibly bright objects. So we assumed they must be close. We looked at the spectral lines, the absorption lines, and they were like absorption lines we've never seen before. So these were mysterious objects that contained new elements. Turns out that actually, if you've got your absorption lines here, and this might be a star, a nearby galaxy, or a distant galaxy, so we thought they were quite near. But it turns out it was very, very distant. So this line I should say, ended up being here. But it flummoxed scientists really, because it moved so much. So they didn't recognise it as well, it didn't make sense. Because if it's close, it couldn't have been shifted that much. Turns out it is just that far away. It is just redshift that caused that to happen. But that put it at the edge of our universe. So how could it be so bright? How could it be so energetic? But it turns out it is. And it's down to having one of these supermassive black holes at the centre, giving off huge amounts of energy. Okay, now I'll finish with this, but it is really important. So you can't skip through this. This is the part which will get you the most exam marks, I suppose. So you will get asked about dangers from supernovae. That would be gamma ray bursts. So you need to be aware of gamma ray bursts. You need to know that the focused huge amounts of energy could affect life on Earth. You need to be able to answer questions about black holes, the definitions of the black holes. You need to be able to talk about what a neutron star is and what are the main properties of a neutron star. It's fast spinning, it's highly magnetic. But this is the equation for a black hole, and this crops up quite a bit. So you have a radius here for the black hole, the distance from the singularity to the event horizon. That's known as the Schwarzschild radius. I think it was Carl Schwarzschild who did a huge amount of work on this. So that's equal to 2 multiplied by g, that's just the gravitational constant from Newton's work, multiplied by m, that's the mass of the black hole, divided by the speed of light squared. So that gives you the radius of a black hole. Now don't think they need to be that massive. Don't forget that a normal star will shrink down as it becomes a black hole. Mass is sometimes given to you, but very often it's given to you as a multiple of stellar masses. So it'll say a star 50 times the mass of the sun collapses into a black hole. So there you can look up the mass of the sun in your datasheet and then multiply it by 50, and that gives you the mass. Okay, so there are plenty of exam questions that ask you to use this equation. So this is the equation for the black hole, and it is in your datasheet. That's it for black holes. Hope that was helpful. Thank you very much.